Hello, my name is Atul Mody. In this session, I'm going to talk about approximations used in physics and errors in estimating physical quantities while we perform experiments. To start with, we say that for small angle theta, if we measure angle theta in radians, then sine theta is nearly theta. So I would like to ask you, up to what values of theta is this approximation valid? And if it is valid, what does this mean for cos theta? Do we consider cos theta as 0 for those angles? You may use your calculator and check for some values of theta. Many times when this question is asked, some students at 10 degrees, some students at 15 degrees. So let's see actually what are the values for which we can assume sine theta nearly theta. So here are the values table. Okay? For theta starting from 0 degree to 30 degree converted into radian, and look at the values of sine theta and cosine theta. So if you look at even 1 degree, you see the first 5 digits, 4 digits are same. The fifth digit starts differing up to 0.0174. They are same whether it is sine theta or theta, but the fifth digit definitely is different. And then this actually increases as your theta increases. So you go to 10 degree, then first 2 digits after decimal are same, third digit differs. And if you go to 30 degree, the first digit is same, second digit definitely differs. And for none of these values, not even for 1 degree, cos theta is, it is definitely less than. Now, in that case, are we justified in saying that sine theta can be taken as theta? Let's see how our computer or calculator evaluates value of these functions. So for example, if I have a function 1 upon 1 plus x, I can express it as a series 1 minus x plus x squared minus x cubed and so on. All right. And for very small value of x compared to 1, we can approximate this series as just 1 minus x. Here, of course, we will assume that the value of x squared is very small compared to x. How small? We'll talk about it. Similarly, if I have 1 minus x, I'm sorry, there is a mistake. On the right hand side, it should have been 1 plus x. It's a series 1 plus x squared plus x cubed and so on. Should be equal to 1 plus x as an approximation. If I have a sine x, I can write a series value x minus x cubed by 3 factorial plus x raised to 5 by 5 factorial, all odd powers of x with alternate signs. And then when we say that this sine x is x, what we are saying is it means x cubed and x raised to 5 terms are negligible in comparison with x value. Of course, you should know that 1 radian, this formula is valid when x is in radian, and 1 radian is nearly 56, 57 degree. And therefore, when I say x is very small compared to 1, okay, it could be very small compared to 56 degree. Okay, but how small? When can I assume that I can ignore x cube? We'll discuss. And similarly, if I have a cosine x series, I can approximate as all even powers. And then, of course, I can approximate it as 1 minus x squared by. Similarly, if I have a function e raised to x, then that also has a series 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on. And again, the same logic. If x is very small compared to 1, I can approximate this as 1 plus x, ignoring square and higher order terms. Remember, if the number is less than 1, then square is even smaller and the cube is even smaller than square. And therefore, those numbers, if they are reasonably small, how small? We will be talking about. So for all these approximations, we must have x very small compared to 1. Now let's say we calculated sine theta for angles up to 30 degrees. So if you take 30 degree, which is pi by 6 radians, theta value is 0.523598 and sine theta is 0.5. What is the difference between them? The difference between them, sine theta and theta, is about 4%. Theta is 4% higher, at a little more than 4%, 4.6, 4.7% higher than sine theta. So if I am taking this as an approximation at 30 degree, I'm assuming that I need my answer accurate up to 4%. So within plus or minus 4%, whatever answer I get is acceptable to me. Then I can say sine theta is okay. This difference will be smaller for smaller values and would start increasing as you go to higher and higher values. So depending on the accuracy, we should say sine theta is same as theta within these many parts. Okay. In this case, if you take term theta cubed by 6, next term after theta, next term is theta cubed by 6, it's 0.024, which along with higher order terms can be ignored if 4% difference is acceptable. If it is not acceptable, we need to bring this 0.024 and we need to subtract from theta, and then we'll have to add theta raised to pi by 5 and so on. So in that case, we should get the desired result. If you can convince yourself by just the value which I showed you calculated, you can use your calculator and calculate. Then at 10 degrees, sine theta is theta with accuracy of 0.5%, half a percent difference between sine theta and theta. So whatever function I am taking sine theta, and if I say that this theta, sine theta is same as theta, then this value is off from the actual value by only half a percent. If that is acceptable, then my approximation is at 30 degree. If you look at cos theta, that's 0.866. Whereas if you take 1 minus theta square by 2, that's 0.863. So definitely here the error is 0.35%. The next term is theta raised to 4 by 4. Actually, it should be theta raised to 4 by 4 factorial, and that would be even smaller than 0.003. And you can check the same thing for 10 degree. Now let's take some examples where such approximations are used and they have a meaning. So let's take a problem. Okay. Here we are assuming that Earth to be a perfect sphere of radius 6,400 kilometers and Mount Everest has a height of 8 kilometers. So find the greatest distance on Earth's surface from where Mount Everest will be visible. Okay. Of course, as you go further and further away, slowly you start losing the sight of the base, but you will still be able to see tip of the mountain. And then, of course, the farthest point from where tip is visible. That's what we want to see. All right. So that's the diagram. I mean, you can see here that this H represents height of the mountain. Capital R, slightly exaggerated diagram. Let's look at 8 kilometer versus 6,400 kilometers. Capital R is almost 6,400 kilometers. H is very small compared to that, which is just 8 kilometer, but just to understand the diagram. So if I look at from a point where The line joining Earth's surface and the tip of the mountain becomes tangent to the surface. That's the farthest point from where tip will be visible. If I go beyond this point, tip will not be visible. And then on the surface of Earth, this distance S, which will be, of course, as you know, the simple geometry, will be r theta. And if you understand that this line which touches Earth's surface, okay, starting from tip of the mountain, is a tangent, then it's perpendicular to radius. And therefore, this r plus h becomes the hypotenuse, and r plus h cos theta is nothing but your radius. For h, of course, very, very small compared to r, you can write cos theta as r upon r plus h. And that, of course, you can check yourself that for h upon r, very, very small compared to 1, I can divide numerator and denominator by r. Then I'll get 1 upon 1 plus h by r. That will be nearly same as 1 minus h by r. Okay. And we use this where we have used this approximation shown earlier. Okay. Now, you got cos theta as 1 minus h by r. Remember, cos theta also in approximation is 1 minus theta square by 2. And therefore, here you can see comparing the two, theta square is nothing but 2h upon r, which is 16 upon 6400 or 1 by 400. So that you get theta as 1 by 20 radian or 9 upon pi in degree in value. 9 by pi is a number which is less than 3. So this is less than 3 degree. If that is your theta, then the distance s on the Earth's surface will be r theta, and it turns out to be 320 kilometers. So if you are at 320 kilometers from base of the Mount Everest, you will be able to see it. If you take the exact value, you would have got cos theta as 0.99875. That would have given you theta as 2.863 degree or 0.04997 radian. SS 319.8 kilometer. And if you realize the difference is only 0.2 kilometer, that's 200 meters. In 300 kilometers, 200 meter is a very, very small value. So you can see it's not even half a percent. It's not 0.6. It's 1/10 of 0.6%. So it's 1/10 of half a percent almost. Okay? So our approximation is fairly good. And you can see here that justifiably the higher order terms can be. Now, you often talk about infinities in physics. There are many expressions. We say we'll wait for infinite time, this will happen after infinite time. Then in our lifetime, does infinite time mean anything? What this infinite time will mean? Let's see. So just look at the equation. This n equal to n0 e raised to minus lambda t is an exponential decay equation. So here it tells you how many radioactive atoms will be without decay, would have survived, and how many would have decayed after time t. If n0 is the number of radioactive atoms I start with, then after time t, I would be left with n as the number of radioactive atoms. Others would have decayed. N0 minus n would have. If I take Q equal to capital Q 1 minus T upon RC for an RC circuit, charging of a capacitor, then here we say that small q will be equal to capital Q as T goes to infinity. There we would say n goes to 0 as T goes to infinity. That means none of the atom would have survived. All would have decayed if you wait for infinite. If you take LR circuit, then the current when you supply DC power would also be given by this kind of exponential expression. So current grows, and we say that after infinite time, current would have reached value E by R. Now, when we say what is infinite time, it's a long, long time. what does it mean when we say log n? Now, here, these quantities, 1 by lambda, or in the second equation, RC, or in the third equation, L upon R, have dimensions of time, and they are called time constants of the equation. In case of electric circuits, they are called time constants of the circuit. Here it is having some different meaning. Okay, 1 by lambda is called the mean life of a node. In each case, we can write time constant as tau, and therefore the exponential term will become e raised to minus t by tau. As t goes to infinity, of course, as you see, e raised to minus t by tau goes to 0. Now, what happens to e raised to minus t by tau when you take t equal to tau, 2 tau, 3 tau, 4 tau, 5 tau? Values are, as you can see, 0.36, 0.1353, 0.0498. E raised to 5 is 0.006. So, if you look at this, 0.018 is still 2% of 1.8%, still 2% of. But if you look at this is 0.67, okay, slightly more than 0.5% of 1. And therefore, for many practical purposes, 5 times time constant turns out to be a good enough, okay, as an infinite. So somebody says wait for infinite time. Well, you have to wait for 5 time constant, 6 time constant, and you are almost there where you should be. Okay, so system would stabilize for all practical purposes. So somebody says, say uranium has a half-life of 4,500 years. All right, then almost 5-6 times that 4,500. So around 30,000 years, most of the uranium would have decayed. Of course, in case of radioactive samples, you deal with very large number of atoms, and therefore even when I say 0.5%, because number of atoms are of the order of 10 raised to 23 to 26 depending on the quantity, and therefore even when we say 1% of it, it would still be just 100 times small. Okay, so there it makes a difference. So it depends on what you are dealing with. But if you are talking about electric circuits and you know that time constant is, let's say, 1 minute, then after 5-6 minutes, your circuit would have stabilized. Okay? If the charge had to grow, if the voltage across capacitor is increasing and reaches maximum, it would reach maximum within 5 or 6 seconds. In case of LR circuit, the time constant is for 1 minute, 5 to 6 minutes, your current would have reached maximum value E by R. As the measuring instrument may not be sensitive enough to record 0.7% variation, even when we say e raised to x goes to 1 as x tends to 0, since e raised to x is nearly 1 plus x, the value of x determines the limit of approximation. Another example is the tides. When do we worry about? How do we understand tides? So let's take, if I take gravitational acceleration near Earth's surface, considering mass of Earth as 10 raised to 26 into 10 raised to 24 kilogram, and radius as 6.4 into 10 raised to 6 meters, as you can see, the gravitational acceleration turns out to be around 9.8 units. That's meter per second. Then why do we here ignore effect of sun and moon near Earth's surface? Because we are in the vicinity of sun. Sun is a huge, very massive. Mass of the sun is million times more than mass of Earth. It's 2 into 10 raised to 30 kilograms. Okay. In moon, mass is of course less than Earth, but it's much closer. I mean, if you look at size of sun and moon, they are almost the same. That's why during total solar eclipse, moon manages to cover entire sun. So in that sense, their effect should be almost similar. So let's check what happens to their contribution. For Earth, you have m upon r square value. Can you see? In G, you have m upon r square, which is around 10 raised to 11. If you take effect of sun near Earth's surface, that m by r square is around 9 into 10 raised to 7, or you can say almost 10 raised to 8. That's almost 3 orders of magnitude smaller, 1,000 times smaller. The effect of sun at Earth's surface is 1,000 times smaller than that of Earth's gravity. And if you take moon, it's 10 raised to 5. So it's even 100 times smaller than the effect of sun. And therefore, for all practical purposes, we take acceleration due to gravity as 9.8 meter per second square. We ignore that we are actually in the vicinity of sun or moon. But that is because we are talking about small masses. Now look at this. When it comes to force on large masses like Earth and its ocean, even tiny effect can prove to make significant difference. And due to size of the Earth, it can cause tides in the ocean. Let's understand how it does. So we want to understand these tides and oceans based on Newton's law of gravitation. Okay. So we need to know what is the distance of Earth from Sun. It's about 500 light seconds, which means light takes 500 seconds to travel from Sun to Earth. Distance turns out to be around 1.5 into 10 raised to 11 meter. Mass of the Sun is 2 into 10 raised to 30 kilograms. Now look at this diagram. So we have a Sun and we have an Earth. And when we talk about distance, we are talking about distance from center to center, the average distance. But when we talk about gravitational acceleration, here, okay, there will be two places. One point which is nearer the sun, and the other point on the other side is farther from the sun. So if you take the point which is nearer to the sun, this g due to sun is 0.0059. And if you take the point which is farther from the sun, then it is 0.00, okay, I'm sorry. So that's 0.59288, and here it is 0.59278. So 288, 278. The difference is in sixth place after decimal. Should it matter? Look at Earth. Earth's mass is 10 raised to 24 kilogram. So this difference, delta G, is of the order of 10 raised to minus 6 centimeter per second square. Or in meters, it would be 10 raised to minus 8 meter per second. So considering mass of the ocean, which is fraction of Earth, this generates a huge difference in the force causing tides. If you take moon, Earth-moon distance is 384,400 kilometer, and you can calculate similar difference. Now, if you look at relative position of sun, Earth, and moon, then you can estimate what is the cause of this tide. Because ocean on one side is a huge mass, it will experience force towards sun. Considering the ocean on the other side is again a huge mass, it will be attracted towards the sun by less amount. Or in fact, if you take center of Earth, okay, ocean on the side of the sun will be attracted with greater force towards the sun compared to center. The other will be attracted by less. So that difference of the force will cause oceans to move away from the center of the Earth. If you look at from the reference frame of the Earth's center, then both the oceans will slightly move away. We call that as high tides. The high tides occurs when sun is exactly above the ocean, on the same side as the ocean, or exactly on the opposite side. The effect is still there if it is on the other side, but then there is a component of the force and the effect is slightly reduced. Okay, so considering relative position of Earth, Sun, and Moon, you can estimate magnitude that causes tidal effect. And this effect, as you can very well understand, will be enhanced when sun and moon are both on the same side. That happens on the new moon day, or when they are on the opposite sides. That happens on a full moon day. So these are the 2 days when the tides are at its peak compared to tides on the other days, compared to what you can call as first quarter or third quarter. Okay. Now let's talk about errors. When we do a physics experiment, we determine value of some physical quantity based on our measurements of some other quantities which are measurable. Okay. Uh, and at the end, we are not sure whether our measurements were very accurate and the estimate gives us the correct value that we determine. We never know, right? So that's always a mystery. And for that, we have to do some other things to realize how accurate is our value that we determine from the experiment. Let's take an example of finding acceleration due to gravity, measuring acceleration due to gravity by using a simple pendulum. You just suspend a pendulum and the bob oscillates and you measure its time period. And the time period of the oscillation of simple pendulum of length L is given by this formula. T equal to 2 pi, sorry, it's printed as 4 pi, it's 2 pi root L upon G. Uh, Experimentally, we take different lengths, and for each length, we measure time of oscillation and calculate G. And with so many such G's found, we can take the average value, okay? And in that average value, we can find what is the deviation from the mean value and so on, okay? We can plot suitable graph also, and using graph also, we can estimate what is the value of G, okay? But how accurate is my value of G that I have found? This is what we would like to. So if we have a physical quantity, W, let's say, that depends on measurement of values of quantities X, Y, and Z, and they are related as X raised to A, Y raised to B, Y Z raised to C. W is X raised to A, Y raised to B, divided by Z raised to C. In that case, what will be the error in estimation of W if I know error in estimation of X, Y, and sorry, error in measurement of X, Y, and Z. This fractional error in estimation of W is because X was raised to power A. So it's A times fractional error in measurement of X, dx by X, plus B times, because Y was raised to power B, B times fractional error dy upon Y. dy was error in measurement of Y. Y is the value of what you measured, and C times dz by Z. Now, although Z is in the denominator, I should have got it minus times C times. But when we actually make measurement, we may make error and measure the value slightly on a higher side or slightly on a lower side. For estimation of error, we always add up these, even if it is going to reduce the error effectively. But estimation of error, we always consider it as with positive sign. So, and percentage error will be fractional error into 100. In case of simple pendulum, this will give you formula dg by g equal to 2 times dt by t plus dl by a. Let's take a typical observation where we find length of 1 meter gives me time period of 2 seconds. This is a typical value for a simple pendulum. So the length of the string of the pendulum is measured using a meter stick. Meter stick has the smallest measurement of 1 millimeter. So my length measurement is accurate up to 1 millimeter. 1 millimeter is 0.001 meter. So if I am calling that as DL, DL is 0.001 meter, whereas L is 1 meter. So this gives me DL upon L as 0.001. If for measuring time period, of course, if I use a stopwatch, it could have a least count of half a second, 1 second, let's say 1 second. And then 2-second measurement would mean it's a huge error. So one oscillation is too quick. So to measure the time period accurately, we say 10 oscillations, 20 oscillations, 50, sometimes 100 oscillations. And you can see what will happen. So suppose if we take 50 oscillations, okay, which in this case will be 100 seconds. So when I make time measurement of 100 seconds, the error could be at the most 1 second. I could be between 100.5 seconds to 100 minus 0.5 seconds. Because I won't be able to read what is between the two divisions. Okay, the accuracy is 1 second. So since I have measured 100 seconds for 50 oscillations, my error would be 1 second in 100 seconds. And therefore my dt upon t would be 1 second in 100. So if I take error, that would be 2 times 1 upon 100, 0.01. So it will be 0.0. Now what does that lead me to? So it gives me the fractional error of 0.021. And if I multiply by 100, that gives me error of 2.1%. So whatever G I calculate from this measurement of L and T will be accurate within plus or minus 2%. The value I have found is likely to be between plus 2 of what I have calculated and minus 2% of what I have calculated. Actual value. Okay. Of course, there are many other reasons we should be worrying about, but this is simple estimation of error of a physical quantity. So since t was 2 pi square root of L by G, G will be 4 pi square L by T square. And that if you calculate, you will get value of 9.869 meter per second. But remember, your time measurement was accurate only till second place. Okay? You had 50 oscillations, 100 seconds with an error of 0.01. And therefore, this G, you should not write as 9.69, you should write as 9. Because your accuracy last digit is the uncertain digit. So this 6 is not certain digit, or 7, whatever you call it. So with error of 2.1%, this gives me DG of 0.207. And therefore, I should say that my G value, which I found experimentally, is 9.87 plus or minus 0.20, which means that actual G value is somewhere between 9.67 and 10.07. This is, of course, based on the experiment we performed and we made. You can have a better quality equipment, you can design better strategies, better techniques for measuring, and come to less error and more accurate estimation of. Is not that formula for this error which we considered is based on differentiation. You realize it was x raised to a, y raised to b upon z raised to c. So when I do dw by dx, it will give me a times x raised to a minus 1 y raised to b upon z raised to c. So when I do dw by w, it will give me a times dx by x. Similarly, d times dy by y and c times dz by z. Right? But this was a very simple algebraic formula. Sometimes you can have more complex situation. But the way to estimate error is to go ahead and use the differentiation. So suppose if I have two resistances in parallel and I know what is the error in R1 and what is the error in R2, then what is the parallel combination giving me? And I should take formula R equal to R1, R2 upon R1 plus R2 and then use the differentiation and then arrive at a formula. I mean, you don't have a general formula, but you do have general strategy, that of a differentiation. Thank you very much.